we've spoken about a load of ZKP technologies this afternoon, and when I think how many of those Ariel had a hand in, well, it's most of them, isn't it? So one earlier speaker said we've got a fire hose of ZKP technologies coming along here, being hosed out. And I think that was a great analogy. I think that's true. But I also think maybe the man holding the hose is this guy who we're going to hear from next. So Ariel from Aztec spoke some years ago now, some years since we caught up. But I'm quite lucky because I get a sneak peek of all the presentations. And when we looked at his, the R&D team here went, "Oh, that's really useful. We can use that." So that's marvelous. So we're off to a winner already. So Ariel, welcome, and over to you.
Yeah, thanks a lot for that nice introduction. So what I'm going to talk about today is a little about the Aztec private smart contract system. I'll talk about that in a very simplified way. And what I'll focus on is a kind of a theoretical framework we came up with that I feel helps like formalize and reason about such systems. So like I said, I'll start with a brief simplified description of the Aztec smart contract system. Then I'll introduce maybe sort of the main theme of this point of this talk is introducing this notion of RCG, repeated computation with global state, which I feel helps reason about and discuss the proving systems underlying such a private smart contract systems. Then we'll get a little peek of how a construction can look using log derivative. And then I'll highlight a little theoretical issue that I'm trying to get cryptographers to look at. I apologize, the door just opened here and I'll have to close it. Sorry. All right, sorry about that. All right, so in the Aztec private smart contract system, similar to Ethereum, Solidity, we have contracts, and the contracts have functions. And the main difference is, since we want to make private proofs about the smart contract execution, each function of each contract will be snarkified in advance, meaning every function will have a verification key associated with it. So for example, here, say we have a contract with functions A and B. So contract A will have function associated with it function A will have associated with it verification key VKA, and B will have VKB. And what can functions do? Well, the main thing a basic ability they have is to call each other. A function in a contract can call other functions in the same contract or in a different contract. So what we have to think about for a minute is when we think of these functions as we do in Snark world as circuits, what does it mean for circuits to call each other? So let's look at a simple example of an execution. Say we start with function A that we called with args A, and somewhere in the middle of this call, there was an inner call to function B with args B. So how do we uh, talk about that in sort of Snark world? And maybe for a second you're thinking, wait a second, don't we already have like such things? Like why is this an issue at all? And the main reason why it's a little new and it's not totally trivial is that in the Aztec world, the functions have already been individually snarkified, meaning associated with verification keys. So the things we usually do, we sort of can't do. What are these things? Well, one thing would be, all right, this whole execution with the internal call, just inline the internal call and think of it as one big circuit without any internal calls. But again, to do that, we'd need to make a new verification key, and we need to work with the verification keys we already had. So what we're going to do is, the basic idea is that A's public input will contain both the VKB and argsb. So a little more specifically, so the proof pi A for A, its public input will be args A, VKB, and args B. And pi B will have as its public input, obviously, args B. And now, so a verifier will check both proofs, and sort of the punchline is that in addition to independently checking both proofs, the verifier will check that the same value for args B and VKB was used in both calls, in both checks. And the idea is that that enforcement corresponds to checking that A called B. Okay, so that's one thing. And now the question is, how, say we're going to have, again, our goal at Aztec is to make a proof, a private proof of some smart contract execution. In this execution, we don't know in advance how many, there may be a long sequence of A calling B, calling C, calling D, a large number of internal calls. We don't know what that call tree will look like in advance. So how can we make a private proof of such an execution? And an important step is all this sequence of internal calls. We need to massage it sort of into an incrementally verifiable computation, just meaning here a repeated application of some fixed function f. So what will this fixed function f look like? So we think of its inputs. Basically, we think of f as a function that like peels things off a stack and each time executes the current function, the current function on it. So we think of its inputs as the current verification key, the current arguments, the next verification key and arguments, a proof pi for the current sort of step, and a stack. And what F will do is we'll check that VK cur and args cur are really the top element in the stack. And it'll take it, sort of pop it off the stack. And now it will sort of execute the current function. So it will check that the proof pi with the current verification key and like the current public input accept. And then it will push VK next, args next to the top of the stack. Right, so that sort of corresponds to, right, in thinking of this function capital F, we can think of an execution composed of many internal calls as just repeated application of this F. Okay, so that seems to work. But so far, we haven't dealt with global state. Contracts, in addition to having functions, also have notes representing the contract's current state. So, for example, a contract can have notes N1 and 2. And in addition to functions being able to call each other, a function can, in the Aztec system, add, read, or delete contract notes. So to enable these operations on the global state, to enable node operations, we will add to the public inputs of these function calls node operations with timestamps. So, for example, if A read the node N at timestamp 8, we'll add this tuple read N8 to the public inputs of A. And if B added node N at timestamp 3, we'll add this tuple add N3 to the public inputs of B. And here sort of an issue comes up that we need to deal with. Where you could say the order of execution is different from the order of proving. So since we've already individually snarkified the functions into verification keys, although in the actual execution, right, we start from A, go into B, finish B, go back to A, we can't do such a thing during proving. We have a verification key for A. We need to do all the proof for A. We can't do it in the middle and get into B. So when verifying the proof for A, which now has in its public inputs this read N8, we don't know for sure that in a future iteration of this proving process, we will indeed see a creation of a node N with an earlier timestamp. So we don't know when we're verifying the proof for A that we cannot determine if this read N8 is valid or not. So to deal, a convenient framework to deal with issues of this form is this notion of repeated computation with global state. It's very simple to what's called IVC, which I'm guessing some of you have heard of, what stands for incrementally verifiable computation, with two modifications. The first one is that in RCG, I can assume the computation ended before the proving starts. If you look at the original IVC paper of Paul Valiant, he's talking about a computation humanity is doing for generations. But in practice, if you look at the literature, we're using IVC in many cases for scenarios in which the computation, it's totally practical to assume it's ended. And we can leverage that to simplify the proving process. The second difference is that the prover memory is allowed to depend on the size of global state in addition to memory for one iteration. So a lot of the motivation for IVC is to capture small memory requirements for a SNARK prover, saying usually saying the memory should depend sort of solely on the size of the transition function we're repeatedly applying. And here we slightly make this more flexible and say prover memory should mostly depend on the size of the transition function, but we allow it to also depend on the size of this global state, which we think of as sort of smaller, is relatively small compared to the size of the whole transition function. Well, small. Okay, well, we'll see this more clearly in the next slide. So to make it more clear, let's give a simplified version of the formal definition. So for an RCG, we think of it's defined by a transition predicate and a final predicate, capital F and small f. And given these, we define, and the relation defined by the RFF is the pairs XW, where X, we think of it as the final state, this Z final, and W is the sequence of Z's, sequence of W's, and a sequence of S's. So we think of the Z's as the different states. We think of the W's as the witnesses that make us move from state to state. And we think of the S's, the SI's, as the little chunks of the global state used in each operation. So we say XW is in the relation if Zn is Z final, so we reached the desired final state. This second thing is similar to what you see in IVC. So for every I, the transition was valid. So F Zi minus 1, Wi, Zi Si is accept. So every transition was valid. And the third thing is what is, different from IVC. We check that if we take these little SIs from all the steps, that the little f of the final predicate holds. The f of all the SIs is accept. And we say a snark is space efficient for this relation if the space required by the prover depends on, again, the transition function plus the size of the global state. So to give some example of the usefulness of this, let's see how we can use log derivative methods to check consistency of node operations. Right, so one thing we want to check is that we're only reading nodes that have really been added at some previous timestamp. So to help us, we're going to in an add operation, we're going to also write down the number of times a node is going to be read. And in the read operation, we're going to actually write down both the timestamp where the node was read, but also the timestamp AT where the node was created. And we're going to check when we're executing a function that AT is always smaller than T. We're going to hash all the node operations from all function calls to get a challenge beta. So this is exactly the thing you wouldn't be allowed to do in IVC, right? Because this also because you wouldn't know them in advance, and also because the size of this vector of all node operations, it depends on the number of iterations. And now what we're going to do is we're going to check that the sum of 1 over n plus beta AT over all the reads is equal to the same sum over all add operations, sort of normalized by the number of reads. So maybe just one thing to clarify, and maybe that is confusing, right? If you look at the first bullet here, it says for each read we check that AT is smaller than T, and you could think for a second, wait, isn't that sufficient if we check that the timestamp of addition is smaller than the right? But the point is, this is sort of just this AT is just sort of something that is claimed to be the right AT during a read operation. It doesn't tell you for sure that this add operation with this timestamp AT for this node really exists. Okay, so I'll just give you a few more seconds to look at this. All right, so I'm going to leave some time for questions because I saw there were a lot of questions in the talk before me. I'm going to skip the this theoretical interlude I mentioned, and just let me just say that, yeah, for more details, please look at the paper, and yeah, and thank you, and I'm happy to take questions if there are any.
Okay. Well, actually, Ariel, there aren't any questions.
Oh.
So I take that to
Murphy's Law, kind of.
Always the way, isn't it?
Yeah.
Always the way. Never mind. That was utterly brilliant. Thank you. And that was an incredibly clear explanation of something that's really complex. Even I felt I understood it. And if I can understand it, then I'm confident the real mathematicians in the room can understand it. So that's brilliant. And actually, a very useful way of assisting with things like composability and such like. Really, really good. Thank you so much. So we're almost on time actually. So I think we'll finish there. And just to say thanks very much for your talk. Really appreciate it.
Thanks for having me.
No problem. And I hope you'll come back next year.
Sure.
Okay. So, well, that brings us to the end of day 3 of the summit, the technical day, and in fact, the end of the summit. So, it's really just down to me to close out, and then we can all go and have a beer, because I think we've all learnt one. So, I think we've all learnt a lot. I certainly have, and I find it. What I like is when it's a very eclectic mix of things, different technologies, different depths. I think that then there's enough for everyone if we have that, and I think that's worked this year. So I hope you'll be back in 2026. It is free after all. I'm not sure where it'll be from. I've heard rumours of New York, but they are only rumours, but we've had fun in Amsterdam this time around. So I think that might even be the 10th anniversary. It's the 9th or the 10th, certainly. I'm afraid I won't be with you because I'm actually retiring. So somebody else will take this seat next year. So expect an uptick in quality of service. That would be my main takeaway from that. And it just remains for me to thank everyone and say we'll see you all next year.